depending on only x, y and g, and same way this b was depending on only x, y and g, and this c was depending on only x, y and g. For this partial differential equation, a of p plus b of q is equals to c. So we have three ordinary differential equation in three unknown variable x, y and g. So this was a coupled first order ordinary differential equation in three unknown variable x, y and g. And we know that if a, b, c are ellipsis continuous, then we can solve this for x, y and g, and we can get the solution in x t comma s, y t comma s and g t comma s. However, what happens in the characteristic methods for nonlinear first order PD? Here we get ds over dt is equals to f of p, dy over dt is equals to f of q, dz over dt. What was the parameter, t or s? What the parameter I told? T. I just changed the parameter. I am just proceeding in the way of the notes which I have provided to all of you. And P, Fp plus Q, Fq. What is the F? This F, I have written capital F. You can take small f, it doesn't matter. So this F is this nonlinear partial differential equation. This F is this nonlinear partial differential equation. Nonlinear means it is non-linear in P and Q. And what is your P? Your P is del Z over del X and Q is del Z over del Y. So this is non-linear in P and Q. It means the derivative of this function Fp will be either function of P or function of Q. Similarly this and similarly this. It means we have three unknown variable x, y and z, and we also have two unknown variable p and q. So to complete this equation, we write the characteristic equation for the Monge generator. And this was dp over dt equals to minus fx plus p fz and dq over dt equals to minus fy plus q fz. So this is the set of characteristic equation. This is the full set of characteristic equation for a fully non-linear partial differential equation given by this. This is a full set of characteristic equation. Basically, it is also known as Cauchy method of characteristic. So this is a set of characteristic equation for non-linear first order partial differential equation. We need 5 equations here because this is going to be function of p or q, this is going to be function of p or q, and in the same way. So we will have only 3 equations in 5 variables. So to complete this equation, we use the equation for the generator of the Monge cone, and we get these 2 equations. So using these 2 equations, we will get the form of p and q, and then we can use those form of p and q in this to calculate the solution. Now, if we have given an initial condition, to solve this equation. So what will be the form of the initial condition? Z at x and y is function of x is equals to z naught x. So this will be initial condition. Now you can see that here we have 5 equations and we have initial condition on only 3 variables. Suppose if we take this gamma x equals to xi, then y will be y of xi and z will be z naught of xi. However, we have 5 set of ordinary differential equation. Here we have 5 set of ordinary differential equation and we have only 3 initial condition. We have the initial condition defined for only 3 variable. So we need 2 more initial condition to fulfill this equation. So to get 2 more initial condition, what we do? We use characteristic strips. We use the equation of characteristic strips, and at s equals to 0, and using this characteristic strips we get 2 extra condition, and then we have 5 equation five ordinary differential equation with five initial condition, like the initial condition defined for all the five unknowns. So we solve this system of five ordinary differential equation using the method of, either you can say the linear algebra, or you simply can solve one by one, and then we find x, y, z, p, q. If the solution exists, so z will be coming in the form of t comma xi. If the solution exists, so this z, t comma xi Jacobian will be non-zero, and consequently we can write z x comma y. So this is the only difference between quasi-linear and fully non-linear. So every time when you get a question, just be prepared in your mind what have been asked and how to respond those questions. So yesterday we solved two questions. Today again we are going to solve some question. So the question is p square plus q square is equals to 2. Find the characteristic of the fully non-linear PDE. Fully non-linear PDE, p square plus q square equals to 2, and determine the integral surface which passes through the initial data x equals to 0 and z equals to y. So what we have? We have f x y z p comma q equals to p square plus q square minus 2 equals to 0. We have the initial data, initial curve gamma is equals to x equals to 0, y equals to xi, and z equals to xi. We have this initial data. This is at the parameter t equals to 0. This initial data is defined at the parameter t equals to 0. Now, using the strip condition, we will find the initial condition for P and Q at t equals to 0. So, what was our strip condition? The strip condition is at t equals to 0. Del z over del g. So, del z over del t is equals to P naught dx over dt at t equals to 0, at t equals to 0 plus q naught dy over dt at t equals to 0. So del z over del x dx over dt, del z over del y dy over dt. So del z dz over dt, sorry, this will be xi. So this is 1 p naught into 0 plus q naught into 1, that is q naught equals to 1. If I am wrong somewhere, then please knock me. Now using this q naught equals to 1 in this equation, we will get the value of p naught. So p naught square plus q naught square is 1 equals to 2, that is p naught square equals to 2 minus 1 equals to 1. So p naught is plus minus 1. So we have two strip condition. Earlier in the problem we are so lucky that we got only one strip condition, but here we are getting two strip condition. It means we have two set of initial data. Now we have to verify, like we will see which one is giving us the solution and which one is not. It might be possible that both are going to give us the same solution, so it will not be a matter of fact. But if p naught is equals to 1 is giving us another condition and p naught equals to minus 1 is giving us another solution, then we will also do that. Okay, so what we have x equals to 0, y equals to xi, z equals to 0, p naught equals to plus minus 1, and q naught equals to 1 at t equals to 0. Now we know that the set of characteristic for this fully nonlinear PDE, which is this, the set of characteristic for this non-linear PDE is, what was the set of characteristic? Dx over dt is equals to f of p. So f of p will be 2p. dy over dt equals to f of q. So what will be f of q? 2 of q. dz over dt will be p f of p plus q f of q. So 2p square plus 2q square. Next, dp over dt equals to minus ff plus p fz. Is there any z? I cannot see, so I think it is going to be 0. Is it? Please verify my calculation. I do a lot of mistakes. Minus fy plus p f of z. And if you have any doubt at any single step, then please ask me without any hesitation. So fy, this is independent of y and this is independent of z. So again it will be c. So from here we are getting p equals to constant. From here we are getting q equals to constant. Now if we use this initial datum, then we will be getting at t equals to 0, constant will be plus minus 1. So p equals to plus minus 1. For sure we are going to get to solution. And this q equals to constant, when we use the initial datum q naught equals to 1, then we will be getting q equals to 1. So from here we can see that del z over del x equals to plus minus 1. So for sure we are going to get to solution. Let's see what happens. Next, using the value of p in equation number first, we will be getting dx over dt equals to plus minus 2. So x equals to plus minus 2 t plus constant. Now at t equals to 0, x equals to 0, so constant will be 0 and we are left with x equals to plus minus 2 of t. And y dy over dt equals to 2q equals to 1. So y equals to 2t plus constant. At t equals to 0, y equals to xi. So constant will be xi. So y equals to 2t plus xi. 2t plus xi. And then please solve it for z. That is very important because basically our aim is to find out the value of z in the term of x and y. So dz over dt gives 2p square is 1, q square is 1. Yeah, that is so cool. So 2 plus 2, that is 4. So basically z equals to 4t plus constant. Again, if we use the initial datum z equals to xi at t equals to 0, so we will get this constant equals to xi, that is z equals to 4t plus xi. Now our aim is to express this g here. What I told you, that we are going to get this function z, where I wrote it. We are going to get this function in the parameter t and xi, but our aim is to find out the unique solution. So for that, this t comma xi can be expressed in the form of x comma y. So we will be getting the solution z of x comma y, and that will give us the unique solution. So this is the most important thing, that between the parameter x, y and t xi, there should be 1 1 onto correspondence. It means the Jacobian of this should be non-zero. So that is the second thing. If we are able to simply write this z as function of x and y, then it would be much better for us. So we can see that y is equals to 2t xi and x equals to plus minus 2 of t.
Hi, sorry for the late joining.
Yeah, no worry.
Yeah.
Okay, so just see this equation g equals to 4t plus xi and see this equation x and this equation y. So if we are taking, let me go to the another page, another it will create a mess here. So we have this z equals to 4t plus xi and we have this x equals to plus minus 2t, x equals to plus minus 2t and y equals to 2t plus xi. So simply we can write z equals to y. Now we need to be careful. If we are taking x equals to 2 of t, then it will be simply y plus x. So you can see y equals to 2t plus xi and x equals to 2t. So it will be 4t plus xi. However, if we are taking minus 2 of t, then z will be y minus x. So that minus minus will be plus and 2t plus 2t will be 4t plus xi. So we have two set of solution. What are the solution? P naught is equals to plus minus plus 1, q naught equals to 1. Sorry. P equals to 1, Q equals to 1. Second, P equals to minus 1, Q equals to 1. X equals to plus 2t, here x equals to minus 2t. Y equals to 2t plus xi, here y equals to 2t plus xi. Z equals to y plus x and z equals to y minus x. So that is, here we are getting the set of two characteristics. We are getting the set of two characteristics. Okay. So from here, if you guys have any doubt in the method of characteristic for the non-linear equation, then please do ask, because that is very important for all of you. Rather, I am going to proceed with the Chapman equation.
Um, I have a question related to the difference between the method of characteristics uh, for quasi-linear equations and non-linear equations.
Okay. So we
Huh?
no nothing. Hello. Yeah, am I audible?
Oh,
Yeah, you are audio.
yes.
I think he has some network issues. Yvonne, can you hear us?
Yes.
Okay. So
Loud and clear.
yeah, so quasi-linear and non-linear equation. That is a very important thing to understand the difference between the method of characteristic for quasi-linear and for non-linear. We already know that the way to express the quasi-linear equation is this. Equals to C. You may turn off your camera so you will be able to hear it very clearly, I think, because sometimes our camera takes a lot of internet. So here we are expressing this del z over del x as P and this del z over del x as Q. However, the non-linear equation is non-linear in P and Q. So it will not be in this form. We simply write it here x, y, z and p q equals to 0. Why we write it in a function form? Because we don't have a specific form for the nonlinear equation. A nonlinear equation may look like this, a nonlinear equation may look like this, a nonlinear equation may look like this. Is not it? So that's why we are expressing it in a general form that it will be non-linear in P and Q. It will be non-linear in P and Q. Now here what we did, we expressed it in the form of direct product of PQ minus 1 with this direction field, So this was normal to the integral surface, because if we say that this is the solution of this Cauchy linear partial differential equation, then the normal to this will be gradient of this function f. And what is the gradient? Gradient will be pq and minus 1. So this was the normal, and because this is the normal to the solution surface, so this will lie in the tangent plane. It means if we are drawing any tangent to a point, so the direction of the tangent will coincide with the instantaneous direction of this vector field a, b and c. So using the method of characteristic, we take any point x, y, z on the solution surface, and we parameterize it like we take r equals to x of s, y of s, z of s. So it is depending
Yeah.
on the parameter.
We first like build like the characteristic how do you the characteristic curve.
Yeah, so characteristic curve. So it is.
And then that will sorry I can hear.
No, just continue.
Ah, then that characteristic curve uh, has to satisfy the equations that actually tells you that it's tangent to the vector field ABC, right?
Exactly. So
And
what technique we use? You guys already know the real analysis. So in the real analysis, if this is the parameter s with respect to x is varying, like if we are drawing a curve between x, the locus of a point which depends on a single parameter draws a curve. So here it is depending on a single parameter, so it will draw a curve, and we know that the derivative of this x with respect to the parameter is limit h tends to 0 x h plus s minus x of s upon h. So if we take this point as x of s and this point is x h of s, so the derivative is when this chord will be the tangent to the curve. When this chord will be the tangent to the curve, that's if h is tending to 0. It means the derivative of the variable x with respect to the parameter is nothing but tangent to the curve. So the curve which will be drawn passing through the point x, y, z, it means the tangent which will pass through xyz will be nothing but the derivative of this position vector. And what the idea behind to write the characteristics? So the derivative of this position vector is nothing but this. And
yes,
now using the idea that this is normal and it is lying in the tangent field, so if we pick up any point x, y, and z and we draw the tangent at that point, so the direction of that tangent is going to coincide with the instantaneous direction of the vector field ABC, because both will be parallel.
at some point, yeah.
Yeah, any point.
Some point.
Choose x, y, z. You can choose x1, y1, z1.
Yeah.
So since this is going to be parallel to ABC, it means this is equals to A, this is equals to B, and this is equals to C. So in this way, we have three differential equations in three variable x, y, z. Now we
can integrate them. You can integrate them and then build the solution.
Exactly, because we are independent of PQ. So we have three equations, three unknown. We will integrate them and we will get solution in three constant. To remove those constant, we need some initial or boundary condition. So that is provided to us. However, what happens in the nonlinear equation? In the nonlinear equation, it is not that much simple what it looks like for Cauchy linear equation. So here the geometry of the nonlinear equation is very tedious. So what we do, we analyze how
the tangent is going to be, so in the nonlinear equation is the tangent is enclosing the solution surface, and the tangent will work like an envelope to the integral surface, and that envelope which encloses the integral surface is going to be a cone. So there was an author,
The Monge cone.
yeah, Monge cone. So in the nonlinear equation, we came across the idea that one of the generator of the Monge cone is going to coincide with the direction of the tangent plane, with the tangent plane passing through a point x naught, y naught, z naught. So suppose this is a surface, like something surface can be like this, can be like this. Now, if a cone is touching this surface at any point, so the touching point, the contact is going to be a line. This contact with the tangent and with this integral surface is going to be a line, and that line is your strip. That line is your characteristic strip. So we use the condition.
It's like the analogous of characteristic curve for the quasi-linear equation.
Exactly. So
Yeah,
we
the
analogous.
the characteristic strip.
Yeah, I would not say that it is analogous because here in the quasi-linear we pick up a point and we took the union of those points, which kind of curve it is drawing. However, here we are not choosing a point, we are choosing a strip, and then we are going to take the union of those strips to find out the integral surface. So there are difference between the quasi-linear and the non-linear. So in the non-linear we use that characteristic strip to find out another extra initial condition. And why it is so? Because here we could see that if we have given this and dz over ds equals to p ft plus qfq. Now we have three unknown x, y, z, and here we can see that because of the non-linearity of this will be function of p or q. P or q, and it might be also be function of p or q, and for the same. So we have three.
Those are the characteristic equations for the nonlinear.
Yeah. So for this we have three derivative of the three unknown variable, but there are five unknown appearing on the right hand side. It means we don't have the knowledge of all the variables. So for that we write extra condition and we use the property of the generator of the Monge cone to write this. And now we have five equations, that is the characteristic equation containing five unknowns. And after solving those five equations in five unknowns, we will get x, y, z, p, q. Using the strip condition, we get the initial condition for p and q, and we already have the provided initial condition for x, y, z, and we club all those initial conditions to find out the acceptable solution of this nonlinear partial differential equation under the given initial condition. So this was the idea. What is the difference between the characteristic of quasi-linear and non-linear? Now we got to know that we have three kind of equation in the first order. Still we haven't crossed the second order. Like we haven't reached to the topic of the second order partial differential equation. We are still at the first order partial differential equation. But here there are three categorization of the differential equation. One at fully linear, second one semi-linear, quasi-linear. I am keeping semi-linear and quasi-linear in the same class, and the third one is non-linear equation. Now we have seen that for the transport equation, that is also advection equation, the solution was well defined. Like the solution exists, it was unique, and it was continuously depending on the initial data. It means the solution was well posed. Next, the condition comes hyperbolic partial differential equation. Hyperbolic partial differential equation. So, a first order partial differential equation, a first order partial differential equation is said to be hyperbolic if it is well posed. If it is well posed, it means the solution should exist, the solution should be unique, and the solution should continuously depend on the initial data. So, a first order partial differential equation is said to be hyperbolic if it is well posed. Next comes the Cauchy problem. Actually, I haven't given the definition in the notes, so for the tomorrow notes, I will write this definition, but I thought I should tell you today, so that's why I'm writing this. So the Cauchy problem, a partial differential equation, del u over del t x, a plus b del u over del y c. A is function of x, y, u. I am taking the Cauchy linear problem. So a Cauchy linear problem, a Cauchy linear partial differential equation defined by equation number first is said to be a Cauchy problem if the initial condition is
For the linear case, we defined a partial differential equation to be just dependent on x and y, right? Not on u.
semi-linear.
Oh, semi-linear. Yeah. Sorry.
And this may be a non-linear in u. This is depending on x, y only, and this may be non-linear. And for fully linear, this may be x, y, and this will be also linear in u. So a Cauchy linear partial differential equation is said to be a Cauchy problem. Is said to be a Cauchy problem if the initial condition is smooth. That is u x comma 0 is equals to u naught x, and smoothness means it belongs to the class of C1. It belongs to the class of C1. What is the Riemann problem? Just pay attention to the definition of the Cauchy problem, Riemann problem. It is very important. Like I can share the the paper of 2023, and you are going to see the title is saying the Riemann problem. So just pay attention to this. So the Riemann problem, this system of this equation number first. So basically a Cauchy linear partial differential equation with piecewise initial data, with piecewise constant data. I would distinguish between the Riemann and the generalized Riemann. So I am saying the constant initial data which is piecewise smooth. So piecewise constant data having a single discontinuity is known as the Riemann problem. That is, here what was the initial data? It was smooth. It belongs to the class C1. It belongs to the class C1. However, in the Riemann problem, ux comma 0 is u minus is constant, u plus is constant, x is less than 0 and x is greater than 0. So it has discontinuity at single point. So this is x and this is 0. So before that this is this line or this is this line. So it is constant at x less than 0, at x greater than 0, but at x equals to 0 there is a hole. So this is a Riemann problem. Now if u x comma 0 equals to u minus of x and u plus of x, then this falls in the category of generalized Riemann problem. This falls in the category of generalized Riemann problem. So why it is generalized? Because it has a discontinuity at single point, but the initial data is not constant before that discontinuity and after that discontinuity. However, for the Riemann problem, it was constant. It has a discontinuity at a single point, but before that it was constant and after that it is constant. Is it clear to everyone?
So I don't know how to like think about a constant.
So simply you can, I am defining 0, 1 here. Just before x less than 0 it is 0.
Oh yes. Okay.
Yeah, and here I am saying that it is sin x and then it is a e to the power x, like the way. Actually, I'm going to share this notes as I was removing because I haven't written this in your notes. In the tomorrow notes, I am going to give these definitions, so don't worry about that. So now we have idea what is well-posed, what is hyperbolic, what is initial value problem, what is boundary value problem, what is Cauchy problem, what is Riemann problem, what is the characteristic method, what is the Lagrange's method. Now we are going to see the Chapman method. So before going to the Chapman method, yesterday I asked a favor from all of you that please read the method compatibility condition of 2 PDE. So I believe that you guys have read that topic because that was very easy topic. So on the basis of that I am going to proceed for the Chapman method. So what is the compatible system of first order partial differential equation? So if we have a non-linear partial differential equation x, y, z, p, q equals to 0, it is said to be compatible to another non-linear partial differential equation z, x, y, z, p, q equals to 0 if both of these non-linear equations have the same solution. Both of these non-linear equations have the same solution. So then
just if they have one solution in common, or they have to have like a lot of solutions in common.
For the time being, I am assuming that both have unique solution. I am not talking about their multi-valued solution because when they have multi-valued solution, so we know that if we talk about the solution of any kind of differential equation, whether ordinary or whether partial differential equation, and it has a multi-valued solution, that is physically not acceptable. Although we say that it has a multi-valued solution, but that is physically not acceptable. So to be well posed, at least we talk about the uniqueness. So for the time being, we are assuming that they have the unique solution.
So if, sorry, so I don't understand, like if f and g are partial differential equations, are different, well, yeah, different, like there's no reason to think they are like the same partial differential equation. So f and g are two different partial differential equations. They are compatible if they have a unique solution for both of them in common.
Sorry?
They are compatible if they have a solution in common.
For the multi-valued solution, we can say that they have solution in common. But for the time being, we are keeping in our mind that they have unique solution. And if they have unique solution, and I am saying that both have the same solution, so for sure it's unique solution, and both are equal. There is
Okay.
no solution like we need to think about the second solution. So when you will read the derivation, it is very easy, and to be F to be compatible to G, we have an compatibility condition. So if you want to check which two PDs are compatible to each other, if I am giving you two PDF and G and I am asking about their compatibility, then you just need to check this condition. You just need to check this condition. If they are satisfying this condition, then those PD are compatible and both of them are having the same solution. So we are going to derive the Charpit equation to solve a fully nonlinear partial differential equation. There are some questions in your notes. You can solve that to get the idea of the compatible condition. So I have given this question so that the following PDs are compatible and hence find their solution. So I have solved this here and you can take a look, and I have also written the Charpit method, and we are going to solve some question based on the Charpit method. But that is the most easy topic which we'll be finishing today. From tomorrow on we are going to study some advanced topic and be ready with the previous topics. So in this section we will discuss a general method for finding the complete integral or complete solution of a nonlinear PDE of first order of the form f x y z p comma q equals to 0. So this is a first order nonlinear partial differential equation. This method is known as Charpit method. So the basic idea in the Charpit method is to find out a compatible PD to this equation number first. So our basic idea here is to find out a compatible PDE which is compatible to given nonlinear PD, and then we will find out the solution of that simpler PD, and that will be the solution of this PDE. So the basic idea in Charpit's method is the introduction of another PDE of first order of the form Z x y g p q equals to 0, and then solve first and second for p and q, and if we know what is p and what is q for any nonlinear or quasi-linear PD, then we know that the solution are going to be of the form of this. Is not it? And if we know what is this, then the total derivative will be del z over del s dx plus del z over del y dy So we know P and we know Q. We know P and we know Q. So dc will be P dx plus Q dy, and now we can use the Lagrange's method to find out x, y, and z. To find out x, y, and z. So and then solve first and 2 for P and Q and substitute. Substitute in this equation. Because in your notes it might be possible that everything is not explained in the detail, but here you are getting the idea how this equation after this equation is appearing. So P now the solution of equation third, if it exists. So every time when we are talking a Cauchy linear partial differential equation and a non-linear partial differential equation whose solution may exist, may or may not exist. We are not sure. So if the solution of equation third exists, if the solution of equation third exists, then z equals to g of x is the integral surface, or f equals to z xy minus z is the complete integral of the given non-linear partial differential equation. Now the main task is determining an equation like Lagrange's method, how to find out the solution without using these tantrum. We don't want to go through these kind of tantrum. We just need an equation and we will keep all the values there and we can find out the solution. Because if we are going to go through this tantrum, so it is easier for us to use the method of characteristic which we have defined earlier and we know the idea. So now, what idea we are using, that for every PDE there is a compatible PDE, and this will be compatible if it satisfies this equation. Now, if we expand this equation on expansion, we have
there's a theorem that assures you that if you have a partial differential equation, you can always find a compatible one, and then that's why we always we can always use this Charpit's method, right?
Yeah. We can always find a compatible PDE, but the given PDE and even the compatible PDE may or may not have solution. So if it does not have solution, so it might be possible that we are unable to find the compatible PDE if we are talking about. Because even for the first order partial differential equation, we don't have the facility of the solution all the time. This is the drawback of partial differential equation. So that's why most of the people rely on the numerical methods. So in the beginning of the class, I announced that on the 13th or on the community state, I told you 13th or 18th. 13th or 18th.
I'm not understanding why. What are you?
Or 18th, 11th September or 18th September. So you need to choose one date between 11th and 18th. I am going to schedule your first exam. So which can be written as, if we will rearrange the terms, so it can be written as, just rearrange the terms. So Fp del z over del s plus Fq del z over del y plus P Fp plus Q Fq del z over del z minus Fx plus P Fz del z over del P minus Fy plus Q Fz del z over del Q equals to 0. Now you can see that this is a linear PDE for which the auxiliary equation will be so this is a linear PDE for which the auxiliary equation is dx upon f of p dy upon f of q is equals to dz upon p ft. I would also tell you something else, and dp over minus fx plus p fz dq over minus fy plus q fc. So this is your Charpy equation. Now there is a relation between the Charpy equation and the characteristic method. So this is your Charpy equation. Charpy's equation. What was the method of characteristic for the nonlinear equation? What was the method of characteristic? What were the characteristic equation? Dx over dt equals to
P F Fp
dy over dt equals to
Fq, and then the sum.
yeah, linear combination with p and q, and dp over dt was minus of fx plus p f of z, and dq over dt was minus of fy plus q f of z. So this is a characteristic equation. Can we write it like dx over fp equals to dt, dy over fq equals to dt, dz over p fp plus q fq equals to dt, dp over minus of fx plus p fz equals to dt, and dq over minus of fy plus q fz over dt. Since this dt should be equal, so this should be equals. This should be equals to this. This should be equals to this. This should be equals to. It means these five inequalities should be equals. And if we keep these five inequality together, if we keep these five inequality together with, then isn't it Charpy equation? And what were we doing in the Lagrange equation and the characteristic method of the Cauchy linear equation? Is it clear?
The last part I didn't catch the revelation of everything equals to dt.
Yeah,
And then
they will be equal.
sorry.
That's why this parameterization is same for this whole system of ODE. So this should be equals.
Yes.
Now I was just trying to remind you how I derived. There were two ways to derive the Lagrange equation. One I use another method, and one I use the method of characteristic. In the same way, here I use the Charpy equation. To derive the Charpy equation, I use the idea of the compatible PDE, and I also use this characteristic equation to write the Charpit equation. Is not it? Just pay attention what I did. So for A, xyp plus B xyzq is equals to C xyz. So this is your Cauchy linear partial differential equation, and the characteristics were for a parameter s. So if we write it like this, so we keep it together because this parameter is same for, and as soon as we keep it together, this is nothing but our Lagrange's equation. Is not it?
Yeah. So the nonlinear method of characteristics, it's like equivalent to the Charpit's method.
In the characteristic equation, we were finding out the solution in the parameter t and xi. So we were seeing the geometry. However, this is not giving you the geometry. We are
Yes.
just
So that's just telling you the Charpit's equation, right?
yeah. That's a Charpit equation that is not going to give us any geometry that will give
The
us.
Monge cone and all of that.
We don't need to go through the idea of Monge cone and their generator, anything. We just know this equation and we will write the solution.
I didn't expect to find the Charpit's equation from the nonlinear method of characteristics.
No, you should expect because you already found out that this equation, the Lagrange.
Well, yes, but yeah, maybe I'm too.
Like everything, by the time you will realize that everything is interconnected, only we need to pay attention to those things because the author who proved the compatible PDE, he did not went beyond the idea of the characteristic. He uses the idea of characteristic and then he finds the another compatible PDE and then he writes the Charpit equation. But he was not explaining the geometry. So firstly, we got to know the geometry of that and then we write the Charpit equation. So every author or every researcher, firstly, they go through the geometry of each thing. Like suppose we are formulating a real life phenomena, we are saying that this is a real life phenomena like shallow water wave. So we say that h is the height of the water. We say u is the velocity of the water, and then we write that if we write some condition and that condition is not coming from that condition is related to the existence, or you can say that the reality. You cannot write the condition without the reality. So we say that h equals to 0. H equals to 0 means the height of the water is 0. It means there is no water. It means that is the dry state. So every time when we write some condition that is related to the physical phenomena, that is related to some situation which we have observed. So most of the authors say that if h equals to 0, then there will be no water. So that is coming from this, that is there is no water. It is the dry state of the ocean. It is the dry state of the river. So in the river flow, in the shallow water flow, we use this condition. So every time when we are writing something that is related to some physical situation, and that's why we are writing. That is nothing, we are just, because if we are writing a random condition, then it is going to be vague in the idea of the physics, because here we are studying the PDE, it means we are studying the physics simultaneously. Next question, we are going to solve a question based on the Charpit method. Although we know how to solve the question based on the characteristic of nonlinear PD, but we will take a look on the question and then you will solve one more question, and then today the class will be 10 minutes longer, might be, I'm not sure. So find the complete integral of find the. So every time when I talk about the complete integral and the integral surface, so try to understand the basic difference between the complete integral and the integral surface. We know that if we have a partial differential equation, a first order partial differential equation in two unknown, in two independent variable x and y, then when we solve that partial differential equation, we are going to get two constants. So a solution which contains a solution which contains this constant and the solution of the form f x y z a comma b, it is not containing any derivatives, equals to constant or equals to 0. So this is a complete integral which is also containing the constants, because we are not provided any kind of initial or boundary condition to remove this constant. However, if we are provided with the initial condition or boundary condition, then these constants a and b will be removed and we will be able to write z as a function of x, y completely. So this is integral surface. So every time if someone asks you what is the complete integral, and this is also known as particular integral. What is the particular integral? It means we have some kind of initial or boundary condition. So this will give us the integral surface. And the complete integral, that it does not have the facility of the initial or boundary condition. So we will get some constant in the solution. So each sentence has their own meaning. Each sentence has their own meaning. You need to identify what is the meaning of this sentence. When the person in front of you is asking something, so what is the meaning of this sentence, what is the meaning of this word, and what is the meaning of, so you need to identify. I need to distinguish which kind of question you are asking to me. So suppose we can simply write it in this form: f equals to p square plus q square y minus q z equals to 0. Then we have f x equals to 0, because we know that ds over dt is going to use fp, fx, fy, fq, fc. So f of y equals to p square plus q square, f of z equals to minus q, f of p equals to 2py, f of q equals to 2qy minus z. Now the Chapman's auxiliary equation, right? Are given by ds over fp dy over fq dz over pfp plus qfq is equals to dp over minus fx plus pfz equals to dq over minus fy plus qfz. So just keep the value. Non-linear first order partial differential equation has its own challenges even to solving these ratios. So it is not very easy to solve these ratios every time. You need to be very tricky and you should know trick how to solve. In India, we use a word named jugaad. So we use this word. jugaad. So what is the meaning of this word is when there is some difficulties or when there is something that you are unable to solve in a straightforward method, then we use something different or some molded method that is not. So we say that we use jugaad, some kind of jugaad. So this jugaad word is very common in India. Like there is something you are unable to go straight forward or to do straight forward, so we make some kind of different thing. And like suppose you want to sit somewhere, you are outside and you want to sit but you don't have chair. So and we find bricks, you know the bricks. So what we do, we make chair from the bricks and then we can sit. So that is a jugaad. So it is a very common word. So here you know, you need to know this jugaad. That looks something fascinating to all of you. That is because a new words, but yeah, it is very common in India because most of the Indian people are. It is said that Indian peoples are very jugaadu. Okay, so if we take look on the class 2, then dp over pq equals to dq over minus p square. So p will be cancelled out with this, and we will get a constant p square plus q square equal to a x constant. Next, p square plus q square, that will be a. So 2ay minus dc and p and q. So p dx plus q dy over 2 p square y plus 2 q square y minus q of z is equals to dz. I'm just using the fractional methods. I don't know whether I am proceeding it right or not. I'm just trying to do that. So this will be cancelled out also. It is giving us dz. That is not giving us a solution. So if we use the last with, so dx over 2py equals to dp over p of q. So p will be cancelled out. At the place of q, you can use under root a minus p square plus minus whether you want, you can keep. Now still it has y. Can anyone suggest me how to solve, or can anyone solve it?
That's like the, oh no, that's not the, it's not like arctangent or something like that.
Try to solve it is very easy, I think. So this and this. A divide on question number first and third. So what he is doing, this p square plus q square equals to a. So just using this one. So f equals to a y minus q of z equals to 0, or q equals to a y of z. So p will be under root a minus q square, that is under root a minus a y over z whole square. So a will come outside. No, a will not come outside. So just keep it inside. Now we know the relation dz equals to p dx plus q dy. So use the value of p and q in this equation. So dz equals to under root a minus a y over z whole square dx plus a y over z dy, or z dz equals to under root
az square minus a square y square dx plus ay dy, or z dz minus ay dy is equals to az square minus a square y square dx. How the person is solving it, just trying to do that. Or d a z square minus a square y square, the derivative of this upon a is equals to dx, or a z square minus a square y square equals to upon a equals to x plus b. So we get a z square minus a square y square equals to a of x plus b, or here from here you can get ac square equals to a square y square plus a square x plus b whole square, or z equals to plus minus a y square plus a square x plus b whole square. So this is the complete integral which is containing two constants a and b. Would you like to try another question here in the class? You have 5 minutes. Please try this. Find out the complete integral of this PDE. Please do the question.
Can we see the Charpitz equation? Well, it's in the notes, so.
Sorry? Yeah. It is in the notes, so you can open in your PC.
Yes.
Please do it here so that we can go through the difficulty, what kind of difficulty you are getting.
I couldn't listen to you.
I am saying that please solve the question here. You have 5 minutes so that we can go through the difficulties, what kind of difficulty you are getting.